Thank you very much for inviting me to give this popular lecture. I'm very grateful for this opportunity. In the 20 years or so since my book, Fearful Symmetry, came out, I have given this talk around the world many times, but I realized that this is actually the first time I've given the talk south of the equator. So I'm very pleased to be here, and I would like to talk to you about fearful symmetry and the search for beauty in modern physics. I should also perhaps first say that this is really a popular lecture for the general public. Yes, I have to use this. Because this is actually a popular lecture and given humanities departments to English professors, and it's unlike physicists. They actually read their lectures, which is what I'm going to do. So this is a popular lecture for the general public and not in any way specifically addressed to physicists. So I've given this lecture at different kinds of places, but more at places like various art centers and so on. And never have I given it before so many physicists. So this is a totally new experience for me, giving this talk in front of physicists. So I hope you indulge me. So, as I said, it's unlike our profession. In the other parts of the academic world, people actually read their talks, and in complete sentences. So, I'm going to tell you not about physics, but about why some physicists do physics. So I want to talk to you about the search for beauty in modern physics. The search for beauty is, of course, one of the central concerns of the arts, of literature, and to some extent even of our daily lives. However, probably not many people realize that the search for beauty is also one of the guiding principles of fundamental physics. Einstein once said, "I want to know how God created this world. I'm not interested in this or that phenomenon. I want to know his thoughts. The rest are just details." Now, to be sure, many physicists are opposed to Einstein's remark with its touch of arrogance. Much of the progress in science and technology, especially technology, depends precisely on knowing, quote unquote, this and that Einstein dismissed so arrogantly. And in fact, after my book came out, some physicists have even taken me to task for professing to follow this view. I was criticized in print, in Physics Today, for example. So indeed, there is no doubt that the this and that Einstein dismissed can be truly fascinating. And I, as a working physicist, am proud to say that I have often enjoyed on what Einstein called this and that. Okay. So in fact, right now, for the last couple of years, I've been working on biophysics, which is certainly something that Einstein would dismiss. But today, however, I'm not going to talk about the detailed phenomenon, but I am going to talk about what Einstein would have called fundamental physics. So the goal of fundamental physics is by definition, if you like. So by just using this term, fundamental physics, it already implies that I'm a certain subscription to reductionism, that the laws of nature can be reduced to more and more fundamental level. But that is what I'm going to focus on in this talk. I'm going to talk about search for beauty in the fundamental laws of nature, not in any of the phenomenological laws. So, as Einstein put it, what is fundamental physics? And I think the definition, according to Einstein, again, in an extremely arrogant statement, the goal of fundamental physics is, by definition, to know his thoughts and to know the mind of the creator. So fundamental physicists find it difficult to believe that his thoughts, quote unquote, with a capital H, his thoughts, would be complicated and ugly. And Einstein's biographer, Banish Hoffman, recalled how Einstein felt about this point. So he said, Einstein, when judging a scientific theory, whether his own or somebody else's, he asked himself whether he would have made the universe in this way had he been God. How arrogant can you get? Okay. So this is what we want to think about. Would we have made the universe in this way if we had been God? So this criterion reveals Einstein's faith in an ultimate simplicity and beauty in the universe. Only a man with a profound religious and artistic conviction that beauty was indeed there, waiting to be discovered, could have constructed theories whose most striking attribute, quite overtopping their spectacular successes, was their beauty. Now, when faced with two alternative equations, one ugly and one beautiful, physicists normally choose the more beautiful. It has happened several times in the history of physics that the ugly equation, rather than the beautiful one, agrees with experiment. But later, it would turn out that the experiment was performed incorrectly. The ugly equation was wrong. It has also happened several times that physicists later discovered that the ugly equation is merely an approximation of a more exact and more beautiful equation. So, for example, there is really not much beauty to the equations of Newtonian dynamics. But we now know that Newtonian dynamics is but an approximation to Einsteinian dynamics. There is no reason why the approximate equations of Newton should be particularly beautiful. Why should nature care about those approximations we happen to make for our own convenience? But unfortunately, when you study elementary physics, almost all the equations you encounter are but approximations to deeper equations. And that's why all of you, with a refined sense of aesthetics, may have come away with the impression that physics is rather lacking in beauty. And that's why you stopped studying physics. Now, unfortunately, this audience is the wrong audience. You know, I gave this talk to an audience of English professors, for example. But in fact, as you go on and proceed to study the physical world, at ever deeper levels, you find more and more beauty. Now, I have been talking incessantly about beauty, but what is beauty? ? To paraphrase the opening line of the Taoist scripture, the Tao Te Ching, I may say, the beauty that can be expressed in words is not the beauty. Philosophers pondering the meaning of aesthetics have produced weighty tomes, but an absolute definition of aesthetic values remains elusive. For one thing, fashion changes. And the Chinese character, for example, so let me give you, aesthetic perceptions differ from culture to culture and vary with time. So, for example, the Chinese character, meaning beauty, and I discussed this in one of my books, Swirling Clouds, A Playful Journey Through Chinese Culture, Language, and Food, which was published by Simon & Schuster some years ago, and I'm proud to say was republished as an academic book by University of Washington Press a few years ago. And as you know, Chinese is a pictographic language, and so the character for lamb is derived from this picture. You can see a sort of very primitive picture of a lamb with two horns. And what happened to the stick from this morning? Okay. It's the picture of a lamb with two horns and 4 legs and a little tail. And so it's easy to see that this gets abstracted into this character, which means lamb. And the character for big is just a man that's outstretched with his, to make himself as large as possible. And in fact, I refer you to Da Vinci's drawing of the underlined with the same idea. So eventually, this evolved into the character for big. So in my book, in fact, I show a picture of my son standing like this. And now if you combine these two characters, as you can see, unfortunately, it got smudged. This on top of this, you see that when you combine these two characters, you get the modern character for beautiful. So to the ancient Chinese, of course, a fat lamb is a very beautiful thing. But to refer to a woman these days as a fat lamb is not a very appropriate thing. And so similarly in the West, we recall the paintings of Rubens, and aesthetic perceptions can therefore differ very drastically. And in fact, in painting, different conventions govern painting East and West. So if there is no objective standards of beauty in the world of human creations, what system of aesthetics are we to use in speaking of the beauty of nature? How are we to judge nature's design? So the beauty that nature has revealed to physicists in her laws is in fact a beauty of design, a beauty that recalls to some extent the beauty of classical architecture with its emphasis on geometry and symmetry. So the system of aesthetics used by physicists in judging nature also draws its inspiration from the austere finality of geometry, a system of aesthetics based on the notion of symmetry. As the poetess Edna St. Vincent Millay put it, Euclid alone has looked on beauty bare. So, in fact, after reading my article, somebody from Princeton wrote a poem and sent it to me about how physicists were trying to look on beauty bare. And it was a very humorous poem. Was very, very funny. And so symmetry is, in fact, a central concept in aesthetics and also plays an essential role in art, architecture, design, literature, and even music. So architecture is filled with examples of symmetry, and a particularly striking example is given by this. Now, I'm going to show you a whole bunch of examples here, and that symmetry pervades architecture and everyday life. So here's another example from architecture. Here's a somewhat more unusual example of a door, an entryway. And here's something from everyday life. And in fact, the next transparency shows that people, human beings, even in very rather casual sort of unpretentious settings. Here's a family having dinner, which this photograph was taken in China. You see that the people naturally arrange themselves symmetrically. You see the furniture is arranged more or less symmetrically, and so on. And here's another example. Okay, at this point, you may be wondering about the illustrations. So, in fact, the illustrations were because I gave this talk a few years ago, at the National University of Taiwan. And in fact, the original text of this talk was based on a talk that I gave in India, because it was given at the National Center for the Performing Arts. And this was a very unusual event because I gave the talk on symmetry. So the original article, which you can see I have in my hand, which very stupidly I did not bring a copy. I should have brought a copy. It's actually illustrated completely with Indian art. Everything in this article is the art of India, and it talks about Vishnu and Krishna and so on. But when I gave this talk in Taiwan, they felt that I should change illustrations to something more Chinese. So they had somebody there in the physics department replace all of my illustrations. So I should have gotten some South African ones, but you were the one who was supposed to have produced the South African one. So for those of you who are interested, in fact, my talk is published in New Literary History, which you can look up which is a journal for the humanities. This came from a talk that I gave at the Center for Literary and Cultural Change at the University of Virginia. So since then, since giving this talk in Bombay, in India, I've given it at various other places, like Academy of Arts in Berlin and the National Center for the Arts in Canada. Now, I may just mention for your amusement that this particular trip to India was very interesting. By the way, people ask me why I write popular books, and one of my more glib and joking answer is so that I can get out of the physics department and get away from physicists. And there was an international conference on symmetry, and I was sent by the USA State Department as the American representative because somebody in the State Department, amazingly enough, actually read my book. And so for the purpose of the trip, I was actually considered to be part of the diplomatic service. And so the consul in Calcutta, the American consul, was supposed to come to the airport and meet me. And so this was the first time in my life in which I arrived at the airport with a whole delegation there about to greet me. And during the conference, it was quite amusing because every consulate would give a party every night, and it was unbelievably lavish, and it's a totally different lifestyle. But nevertheless, India was classified by the American government as a hardship post. So I was entitled to rest and recuperation in Thailand, both coming and going, at the American taxpayers' expense. So, and just for fun, and strictly for fun, I will show you a few more examples. Here's an example from religious art. And you notice something very interesting, namely that the overall design is overwhelmingly symmetrical, but many of the details are not. In particular, you will notice the pose, and I don't know if you can see it clearly enough, and it's a very Buddhist pose. If you know anything about Buddhism, you know how you hold your hands. Breaks the symmetry. You put one finger in the other hand. So that's a very interesting example, which we'll eventually come back to. Here's another example, and again, the overwhelming impression is symmetrical, but nevertheless, you would see that in the details on the various objects she's holding, it is not symmetrical. This is a poster that I saw in Taipei for a concert, which I like a lot. It's actually, and has a sense of symmetry, but at the same time, the way it's designed, it has a kind of, it manages to convey a sense of melody and also a sense of music. You notice there are a lot of birds, and the birds also breaks the left-right symmetry. Most of them are pointing to the left. More examples, so I'm just, clearly one can produce a lot of examples. Here's another example a friend of mine thrown in. So the violin is an interesting example. The body is extremely symmetrical, but up here there is breaking of symmetry. Now, so far, I've shown you mostly examples of left-right symmetry. So these are all just a number of amusing examples. But how does the concept of symmetry arise in physics? So, for example, consider rotational symmetry. Just to sort of focus on what we might be talking about, let me show you an example of rotational symmetry from everyday life. This is very difficult to find, but the people, when I gave this talk in Taiwan, they actually found an example of a completely circular house. So this is interesting because this would seem like a very natural way to build a house, to make it circular. But notice, very interestingly, sort of people naturally put the clothesline along the axis of the circle. And in the Indian art illustration, I would say, I might mention that It was a picture of Krishna surrounded by dancing girls. That was an example that was used from India. So coming back to this question of rotational symmetry, what does it mean in physics? It means that the laws of physics do not prefer any particular direction in space. Now, to the rational mind of our generation, particularly the mind entertained by films on intergalactic warfare, like Star Wars and the like, the statement that no one direction is intrinsically preferable to another is almost a matter of philosophical necessity. But this point was far from obvious before. It's obvious to our generation that in space there is no direction. But for the entire history of the human race, until recently, it was not obvious. And for eons, humans thought that up and down defines a special direction. And our understanding of rotational symmetry really only started with Newton's insight. And this is, in fact, one of the greatest insights in the history of physics, that apples do not fall down to earth, but rather towards the center of the earth. So there's a big difference. Apples do not fall down to earth, but rather towards the center of the earth. The words up and down, to paraphrase Einstein about the mind of the creator, the words up and down have no place in the mind of the creator. The creator never heard of the words up and down. So this talk is sort of given to the wrong audience because, this have to be, the English professors are saying, wow, that is amazing. I didn't know that. Okay. And so it is amazing. It is amazing. So let me give you a more precise definition of rotational symmetry from physics. Consider two physicists studying the world, and one of them carries out his observation with his head tilted. Now, because of this, the laws that they formulate are superficially different. But we would certainly hope that physical reality does not depend on the observer. Now, again, it's really funny that people that are not physicists, they think certain things really strike them that doesn't strike physicists at all. Like the statement that I said, one of the physicists carries out his observation with his head tilted. Once when I gave this talk, somebody thought this was such an amazing thing that when the talk was published, on the cover, it was a picture of a physicist with his head tilted. So the laws that the two physicists formulate are superficially different, but we would certainly hope that physical reality does not depend on the observer. Therefore, we should be able to transform the law formulated by one observer into the laws formulated by the other observer. So symmetry implies transformation. Now, this is a very important concept that you English professors better understand. Symmetry implies transformation. I'm going to say it twice, okay? Just make sure you English professors all understand this. Symmetry implies transformation. Got it? Okay. Now, I must emphasize here, and this is a very important point, that I'm talking about the symmetry of the laws of physics and not the symmetry of the phenomena these laws describe. When we appreciate the symmetry of a painting, when we go to the art museum, we are appreciating how the artist arranges the pigment molecules on the canvas. This is the symmetry of phenomena. What physicists appreciate, however, is the symmetry of the physical laws governing the interaction of the pigment molecule, not how the pigment molecules are arranged by the artist. But unfortunately, the examples I can show you are necessarily examples of visual art and of visual and therefore extrinsic symmetry. So in this sense, I would like to say, my desire to liven up the discussion notwithstanding, it may be misleading to provide any examples from the visual arts at all. I shouldn't give any examples from the visual arts because all the examples I can give are of extrinsic symmetry rather than of intrinsic symmetry. So the intrinsic symmetry of fundamental physics can only be seen through the eyes of mathematics. Now, so we must distinguish between extrinsic and intrinsic symmetry. So For example, when I gave this talk at the Canadian National Centre of Arts in Banff, Canada, some woman artists jump up and down after the talk and said, I'm going to go home and try to, I'll paint something that would somehow convey the intrinsic symmetry of the laws of physics. But so far, I haven't heard from her. So it may not be that easy. That it's always an extrinsic symmetry that we see in the visual example. So that we must distinguish clearly between extrinsic symmetry and intrinsic symmetry is of utmost importance. As an example, I may mention that the ancient Greeks were confused precisely because of their failure to make this distinction. They thought that the orbits of the planets must be circles. In fact, the rotational symmetry of the laws governing the gravitational interaction between the sun and the planets does not in any way imply that the orbits must be circular. That is a mistake, a fallacy that the Greeks made. It is perhaps amazing that after some 2,000 years, many people continue to be confused by this point. And almost every layperson I've talked to, intelligent layperson I've talked to, confuses this point. So the orbits are not circular, as Newton discovered. They are ellipses. It's the laws of physics that are rotationally invariant, not the manifestations of the law. So I would like to ask you to keep this distinction in mind, even as I continue, by necessity, to illustrate my talk with examples of extrinsic symmetry. Okay, with this audience, it's completely obvious. I'm just belaboring the obvious. Okay, so what we have learned, and this is the key concept of this talk, is that symmetry implies transformation, as we have already seen, but transformation in turn implies simplicity and unity. So, for example, a physicist and a mathematician would say the circle is simpler and more unified than the square because there are many more transformations that would leave the circle unchanged. You can rotate the circle through any number of degrees, and the circle will be left unchanged. But for the square to be left unchanged, you can only rotate it through 90 degrees. So, if the next important concept is unity, as I've already mentioned, talking about the circle and the square, we can see this concept quite clearly. If the different parts of a structure can be transformed into each other, then the different parts of the structure are unified with each other. So the structure has an underlying simplicity. As an example in physics, consider the fact that before Einstein, electricity and magnetism were described by 4 equations. One of these, for example, states that a magnetic field changing in time generates an electric field changing in space. When I was a student, I had to memorize these equations before every examination. So let's see. A magnetic field changing in time produces an electric field changing in space, or is it changing in time? So I was born with a terrible memory. It was just awful. Before every exam, I have to remember all these horrible equations. Now, however, with relativistic symmetry, one single equation describes an electromagnetic field changing in space-time. So the point is that before relativistic symmetry, before you had the symmetry, we have electric field and magnetic field changing in space and changing in time. But now a single equation describes an electromagnetic field changing in space-time. I find this completely symmetrical equation as easy to remember as the shape of a circle. And intrinsically, advanced physics is simpler than elementary physics, a little secret not often revealed to the lay person. Many people are stumped by high school or college physics because they're presented with misshapen phenomenological equations having little to do with nature's intrinsic essence, with her beauty, her symmetry, or her fundamental simplicity. So let me give you another example to this idea about simplicity and unity and transformation. So the one example I thought of was a Chinese paper cut. So I've covered up part of this paper cup. Okay? So if I tell you how this is made, it's made by folding a piece of paper and then cutting it. Okay? So what physicists are doing is as if they have discovered this part of the drawing, and they're trying to make theories to describe what is on this other part. So now if they have some idea about how the nature is how nature is designed with symmetry, so in this case some left-right symmetry, then physicists can predict what lies underneath here. Okay? So I find it very awkward to give this talk in front of people like Don Maroff, who understands this perfectly. And if I explain this to a humanities professor, they're like going crazy. Wow, So when I ask them to guess what's on this side, they're like, oh, wow, I think I know. There must be another guy over here. So I shouldn't make fun of the English professors. Actually, they're very intelligent people. But, here I'm giving a lecture, a popular lecture, in front of a bunch of non-popular physicists. What can I? Okay. So, well, that's what we always tell the young people, right, going for job talks. Make sure that you give talks at the senior professors at the place you're trying to get a job, understand. Okay. So, I guess you all know what to expect under this piece of paper. So, if we have left-right symmetry, that's exactly what you would expect. Now, actually, at some place where I gave this talk, some young string theorists came to me afterwards and said there was some broken symmetry. Okay, up to this point, the examples I mentioned all describe the symmetries of space and time. The symmetries between left and right, the symmetry of rotation, and the symmetry of motion. Now, you may think that the symmetries of physics have reached a natural end. In fact, it looked that way to many physicists. Well, after we discussed the symmetry between left and right, the symmetry of rotation, the symmetry of motion, as Einstein did in his special theory of relativity, what else is there? What other symmetry is there? Well, it looks like the notion of symmetry has reached a dead end. But not so. A brilliant young German physicist named Werner Heisenberg in the 1930s discovered a new type of symmetry in which one kind of particle is transformed into another type of particle. Now, this transformation does not occur in the space of our daily lives, but in abstract internal space. So Heisenberg noticed that there are two elementary particles known at that time. Some of you may have heard about this in high school. One of them is called the proton, the other the neutron. Now, if you haven't heard of these particles, don't worry about it. Just take my word for it. There are these two particles called proton and neutron. And Heisenberg said, this brilliant young German, whom nobody in the audience has ever heard of, proposed in this internal space, one particle can be transformed into another. So it's kind of like a rotation in some internal space. Now, in this way, an entirely new set of symmetries, the so-called internal symmetries, emerged in physics. And many of the symmetries discussed in contemporary physics are internal rather than external. And it has opened up a vast vista to physicists after Heisenberg. So to summarize, let me emphasize, the symmetry of space-time is limited, but the symmetry of internal space is, in some sense, unlimited. You can invent more and more complicated, not complicated, but bigger symmetries. And in fact, one of the most important calculations in particle physics in the early 1960s is this calculation. And the calculation is 3 times 3 minus 1 is equal to 8. Now, you go home and think about this calculation, and you would realize that it's true. And So, in particular, a very famous physicist called Gell-Mann realized that 3 times 3 minus 1 is 8. And so he wrote a very famous book called The Eightfold Way, in which he predicted that particles should come in sets of 8. So, in fact, we see here a bunch of elementary particles. There's the proton and neutron of Heisenberg. But then there were also other particles discovered. They're called sigma and chi, and never mind what they are. But in fact, there are 8 of them. And in fact, historically, it was very interesting because originally the experiment was wrong. And experimentally, never mind what parity means. It's some technical thing that only physicists worry about. Originally, the experiment was wrong, and parity of this particle was also measured to be plus. So this particle was put onto this side of the page, and people thought Gell-Mann was completely wrong, that his theory was rejected by experiment. There have been 9 particles instead of 8. But it turns out the experiment was wrong, and Gell-Mann did this calculation correctly, and so he received the Nobel Prize later for this work. So at which point the English professors say, oh, it's so easy to get a Nobel Prize in physics. Okay, so another exceedingly important development is the discovery by another German physicist, Hermann Weyl, that electromagnetism contains another previously unknown symmetry. In 1954, Werner Heisenberg, I remind you, Werner Heisenberg introduced the notion of internal symmetry, and then Hermann Weyl realized that electromagnetism contains a previously unknown symmetry. And in 1954, Xian Yang and Robert Mills generalized Heisenberg's concept. In some sense, what they did is they took Weyl's symmetry and synthesized it with Einstein's and Heisenberg's concepts. And in the process, discovering a new type of symmetry known as gauge symmetry. Now, at that time, in 1954, physicists felt that the symmetry was beautiful, but that it did not have any relations to reality. Indeed, it appeared to contradict experiments. Okay, so for the physicists, let me deviate it from the written text. There's a famous story that when Yang gave the seminar at Princeton, 10 minutes into the talk, Pauli said, your theory contains massless particles. Are there massless particles in nature? And Yang replied, no. And then he tried to go on with the talk, and Pauli asked him the same question, and he said no. And Pauli said, sit down, and the talk was over. So so that was the story about the talk. And Merv Goldberger told me that he realized the paper must be important, and so he put it on his desk, but eventually it got lost. So at that time, in 1954, it seemed to contradict experiments. But 20 years later, in 1974, after much arduous and abstruse work by a large number of physicists, the symmetry was discovered to be realized in nature. So this particular chapter of physics may be called the triumph of beauty. Now, when I was gave this talk at the University of Virginia's Humanities Center, at lunch before my talk, I was introduced to a scholar of James Joyce from London. And so I thought to myself, perfect, because I, in fact, quote James Joyce in my book, Fearful Symmetry. So I cannot resist showing you this quote here. So, in fact, James Joyce thought of gauge symmetry long before Yang and Mills. And yes, indeed, long before he used the term, and I will show you the relevant passage in Ulysses. So, this is a dialogue between Zoe and Bloom, for those of you who have read Ulysses. And Zoe said, come, and I'll peel off. And Bloom, filling his head dubiously with the unparalleled embarrassment of a harassed peddler, gauging the symmetry of her peeled pears. and somebody would be, this is a serious talk, I should not burst out laughing. I think it's all Don's fault because I've been learning his laugh the last few days, and so having a lot of trouble. So in fact, James Joyce had this notion of gauge symmetry long before physicists. And so as a result of my lecture, I was later invited to write an article expanding on this theme. So I got to be a James Joyce scholar. So what happened was that I published this article in New Literary History on the female breast, in the symmetry of the female breast. And it actually was a very serious academic article, I assure you. Yes, exactly. Yes, but it was, how do I put it more accurately, it's Gell-Mann discovering James Joyce, right? Discovering the quark in James Joyce. So in the last 20 years, the basic direction of theoretical physics has been towards generalizing the notion of symmetry and discovering ever more abstruse symmetries. Now, this approach is rather different from the so-called quote-unquote scientific method described in elementary textbooks. Physicists would start from an aesthetic consideration and reach a new symmetry, and subsequently they would expend a great deal of energy and effort to determine the consequences and implications of the symmetry. So let me illustrate very, very roughly speaking, and remember I'm trying to explain this to artists and humanities professors, not to physicists. Roughly speaking, the way 19th century physics went was you do the experiments, and then you propose a theory, and then eventually you find a symmetry. So the experiments consist of getting some frogs from the local market and cutting off the leg of the frog and discovering that the frogs were twisting and twitching and so on. And you do various experiments like that, and you with electricity, and then eventually you write down a theory, namely Maxwell's theory, and then you eventually discover the theory contains a new kinds of symmetry that you haven't thought of before. Now, in the mid to late 20th century, this chain of reasoning was reversed. Typically, what physicists did was to write down some symmetry group, which led to some theory, and then eventually check it with experiments. So finally, of course, at some point, physics being experimental science, physicists would need to know if experiments were in accord with these consequences. Now, at this point, some of you may feel, well, this guy is crazy. Surely you're overstating the relation between symmetry and beauty. Now, I get this kind of reaction, especially when I'm speaking to artists. So perhaps you're thinking that beauty in the arts is multifaceted, and art historians have written learned treatises on aesthetics and symmetries, but one aspect out of many. So these physicists don't know what they're talking about. But this is because the symmetry in the visual arts, as I said, is limited to the rather simple symmetry between left and right, or at most circular symmetry. Our common perception of symmetry grew out of our perception of the space we live in. Without the language of mathematics, we find it difficult to imagine symmetries larger and more involved than circular symmetry. Can anything be rounder than a sphere? I ask you to imagine this. But with the use of mathematics, it is actually possible to construct objects that are rounder than the sphere. Now, some of you, upon hearing about larger and more involved symmetries, are perhaps thinking of complicated geometric patterns used in various visual designs. Precisely the opposite. These more complicated patterns, in fact, possess less symmetries. The symmetry of modern physics is elegant, intricate, beautiful, rather than complicated. The beauty that I speak of is that which we cannot see with our eyes. To see the symmetry and beauty of modern physics, you have to close your eyes. But I may be accused of being an arrogant physicist, but when I hear non-physicists talking about symmetry, for example, at that conference held in India, I realize that most of the other participants' conception of symmetry is limited to the symmetry between left and right, or perhaps at most the symmetry of rotation. So, for example, there was one of very famous dancer from India who was demonstrating the classical dance of India and how it was symmetric between the left and right. So I would say to myself, goodness, there is so much more to symmetry than that you have not the eyes to see. If you are serious about understanding the concept of symmetry, please go out and learn about the relevant mathematics. It's not that difficult, and you will grow a second set of eyes. So this is totally... Now, just to let you guys know, this mathematics is called group theory, so some of you may want to go out and learn group theory. Then you'll understand why certain things can be rounded in the sphere. Okay. So as I go on and on about symmetry and beauty, you may begin to feel that I must be talking nonsense. Clearly, one of the consequences of symmetry is monotony. So let me show you some examples once again. Here are some sculptures, and this is left-right symmetric, so it seems, and here's another example, something left-right symmetric. It seems, in fact, a little bit monotonous and somewhat boring and stiff. In particular, look at this guy, right? He looks very stiff. And here's an example from folk art. This is called The Mother-in-Law. And for some reason, many men in the audience seem to feel that the sculpture captures certain essence of the mother-in-law. Now, you see, it's very symmetrical, but also, at the same time, some aspects of it is not quite symmetrical. But anyway, I've made my point, I think, that one consequence of symmetry is, in fact, monotony. So, similarly, if the design of the universe were absolutely symmetric, then the universe would be a rather monotonous and boring place. We would not want to inhabit such a universe. As Einstein said, suppose you were the creator, then you would be faced with an impossible design dilemma. So Einstein was worried about this. On the one hand, you would like to make the universe a fun and interesting place where people would like to visit. But on the other, if your design is not perfectly symmetric, people will criticize your thoughts as lacking in beauty. At least physicists would criticize your thoughts. So what could you do? Now, precisely because of considerations of this sort, physicists in the early 1960s felt that the development of symmetry had reached an end. Because in the early 1960s, people said the universe is obviously not symmetric, and so the ultimate design of the universe could not possibly be symmetric. However, a profound discovery in theoretical physics, which I won't have time to explain, known as soft symmetry breaking, showed that this apparently insoluble design dilemma could in fact be solved. There is a way of breaking symmetry softly in such a way that the ultimate design of the universe can be perfectly symmetric, while the manifestations of this design may be totally non-symmetric. It is a way for physicists to have it both ways. You can write down laws of physics that are symmetrical, but yet the manifestations of those laws are totally non-symmetrical. The symmetry could be broken. In fact, the very term symmetry breaking used by physicists reminds me of a traditional practice in the making of Chinese seals. So this is one example, and give you another example here. Among the art forms of the Far East, the seal is perhaps one of the least appreciated by foreigners. In the Orient, however, the famous carvers of seals are revered as great artists and generally regarded as perhaps one of the highest art forms. There are entire books published in China containing nothing but imprints of seals. and much serious writing is devoted to the aesthetics of the seal. Now, too much symmetry and perfection are considered undesirable. And in fact, after making a seal, a carver would hit the seal lightly with a hammer to produce breaks around the frame. And so you see in this example, things are almost symmetrical, but never quite symmetrical. It's called the aesthetics of the imperfect. Right? So, incidentally, a personalized seal has become a favorite purchase of artists traveling in China these days. So I can easily imagine the scene when a typical tourist picks up his or her purchase the next day. Hey, this is broken. I don't want it. So soon enough, we'll see perfectly symmetrical seals. The story of fundamental physics in the last 30 years or so is largely the story of the discovery of ever larger symmetries. For instance, physicists have found a larger set of symmetry which unifies 3 of the 4 fundamental interactions known in nature into one single interaction. The resulting theory is known as the grand unified theory. And soft symmetry breaking provided the key, allowing physicists to go on searching for symmetries in the ultimate design, even while they observe that the universe is almost completely non-symmetric. Now, as physicists look at nature at deeper and deeper level, they find to their amazement that underlying laws are more and more symmetric. And this is really very remarkable, and it took me a while to find some examples to illustrate this. Consider the ceilings of this building. If you go on the outside, the symmetry is fourfold. It's the symmetry of a square. But as you go in, you see that you have the symmetry of an octagon. And as you go in, it becomes more and more symmetrical. So this is just a pictorial way of illustrating what physicists have found. As they look deeper and deeper into nature, they found that the laws become more and more symmetrical. And in some strange, perhaps coincidentally, the architects of these buildings have a sense, the same kind of sense that the physicists have, that as you go in, things become more and more symmetrical, but at the same time, you're reaching higher and higher, and it's almost going deeper and deeper into nature, into some sense of heaven. And many physicists believe that the ultimate design of the universe should be perfectly symmetric. There should ultimately be just one law, and this remains a belief. Some laws of nature are, in fact, not symmetric. So, for example, in 1956, T.D. Lee and C.N. Yang found that the weak interaction is not left-right symmetric. And this, in fact, shocked the world of physics. But up to now, it has not been established whether this asymmetry is only apparent. So, and whether it actually holds at a deeper level. So, at first sight, the laws of nature seems to be symmetric between left and right, but if you look more carefully, as physicists did in 1956, they discover that it's not exactly symmetric between left and right. So many physicists, there's still an unresolved point and rather controversial, and many physicists like to think at a deeper level, the weak interaction is actually perfectly symmetric between left and right, that the symmetry is just broken. Now, I've saved till the end a mention of the basic symmetry of time reversal. I have saved till the end a mention of the basic symmetry of time reversal because I do not understand it. Neither does anybody else. As a physicist, I know what time reversal symmetry means. The fundamental laws of nature do not pick out a direction of time except in the decay of a certain subnuclear particle, and even then only indirectly. I'm a professor of physics, and so certainly I can talk the talk like everybody else, and so blah, 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 blah. Nature does not pick out direction. But as a conscious being, I know very well that there is a direction to time. So in physics, relativistic symmetry relates time and space. Yet again, as a conscious being, I know that time is different from space. So we're confronted here with a basic tenet of physics, the exclusion of consciousness. The West was able to develop science and technology and triumphed over the East by drawing a line. On one side of this line, the physical world, and on the other, for lack of a better term, the non-physical world. I believe that a deep understanding of time reversal symmetry may take us across that line. With these remarks, I'm taking off my physicist's hat. Some years ago, I was invited to give a similar talk to a conference of philosophers held in Colorado. And I asked the organizers to schedule my talk in the evening because I preferred to remain a physicist when the sun was out. So, unfortunately here, the sun is still out. So at this point, I take off my hat as a physicist, and I'm going to some speculations. The discovery of ever more symmetric universe raises the philosophical question. 20 years ago, the physicist Eugene Wigner, I guess it's now more than 20 years ago because this article was published some time ago, I should mention that some of my thinkings about time reversal is published in this book, which is an anthology of various science writers and scientists on the mysteries of life and the universe. Has this rather pompous title. Not my title. It was chosen by this guy, Shore. So Eugene Wigner wrote a very interesting article which had a deep impact on me. It's called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. He said it doesn't make sense to him at all that mathematics is actually useful in physics. So I feel that similarly, we can ask about the unreasonable effectiveness of symmetry considerations in understanding nature. Why should it be so? Why should symmetry be so relevant for the description of nature? Does the fact that nature becomes more symmetrical imply that there's a design? Einstein once said, the most incomprehensible thing about the world is that it is comprehensible. A priori, we could live in a chaotic universe whose working does not display any symmetry. And in fact, when Einstein wrote this remark, that the most incomprehensible thing about the world is that it is comprehensible, most of the symmetries we now marvel about were not even known to Einstein. So in fact, this Wigner's article about the unreasonable effectiveness of mathematics in physics, this article, on the 50th anniversary of this article, there was a book published to commemorate Wigner's article. And the guy who edited the book asked me to write an article, and my article was on the unreasonable effectiveness of symmetry in understanding the world. I don't know why. So the question of why nature appears to be symmetric is not purely a philosophical question. It can be addressed with more than just talk. Some physicists have suggested that the ultimate law is not symmetric, but that the symmetry appears as an illusion at lower levels of perception. The ultimate design could be chaotic. This view can be mathematically demonstrated to be possible. It is, however, rather unpopular. So here, just for the benefit of the physicists, I'm talking about these unorthodox theories about flowing to a renormalization group, flowing to a symmetric fixed point, but the underlying Lagrangian is totally non-symmetrical. So why is symmetry relevant for nature? So perhaps a rather facile non-answer is that we impose the symmetries on the world in order to understand it. To oversimplify things, I may call this the Kantian view as in contrast to the Platonic view. You see that I have actually, indeed, I was not joking. I have been to a philosophy conference. And in fact, during my talk to the philosophers, someone in the audience shouted out and accused me of being a Platonist. So I thought it must be some sort of horrible insult. But then later, I just discovered that it just means that he was accusing me of being a follower of Plato. So, but in fact, I prefer to follow Kant. So I believe that most physicists would prefer to think otherwise, that symmetries are there to be discovered and not imposed on our description of nature. In this connection, I may retell a fable told by the physicist Arthur Eddington. He said, imagine, he told this following story, in a fishing village, a fisherman managed to formulate a law of the sea after careful study. The law is that all fish are longer than 1 inch. Of course, what he did not realize was that the meshes of his net are always larger than 1 inch. So perhaps symmetries tell us something about the discoverer rather than the designer. My own prejudice is reflected in the title of my book. Fearful Symmetry. I chose this title because I would like to conclude this lecture with a quote from William Blake's poem about the burning tiger. In fact, it rather tickles me that I can be talking about Blake to an audience of English professors. And this is what I said when I spoke to English professors. So, tiger, tiger, burning bright, in the forest of the night, what immortal hand or eye could frame thy fearful symmetry? Now, in fact, the poet hesitated a great deal. If you look at the manuscript for this famous poem, he hesitated a great deal over whether he should use the word could instead of dare. So, could frame thy fearful symmetry, or dare frame thy fearful symmetry. He actually, if you look at the manuscript, you find that he crossed out the words could and then put in the word dare, and then he crossed out the word dare, and he crossed out the words several times. There is, of course, a significant difference between could frame thy fearful symmetry and dare frame thy fearful symmetry. So let me read it to you again. Tiger, tiger, burning bright, in the forest of the night, what immortal hand or eye could frame thy fearful symmetry, or rather, dare frame thy fearful symmetry. So suppose that you were the poet. Okay, I'm asking you much less than what Einstein asked of you. Not to create a universe, but merely to be a poet. Which word would you use? I ask this question of those of you who are not English professors, right? The English professors in the audience probably already know the answer. So, I'd like to propose this. I'll take a minute for you to think about this. Would you use the word could or the word dare? Could frame thy fearful symmetry, dare frame thy fearful symmetry. Okay, I'll now ask for a show of hands. Instead of Don Maroff's method, people are not allowed not to show their hands. Okay, so everyone has to show their hands at least once. I suppose you can show it twice, raise your hand twice. So those of you who prefer could, raise your hands, please. And those of you who prefer dare, well, dare wins out. So, what do you think? Which word do you think Blake used? In the end, Blake hesitated and hesitated. And in the end, Blake used both words. The first stanza of the poem is identical to the last, except that in the first stanza, the word could was used, while in the last, dare was used. Numerous literary critics have analyzed this famous poem, but I particularly like the comments of Lionel Trilling. He felt that up to the fifth stanza, the poet sought to define the nature of the tiger by the nature of God. Right? Could frame thy fearful symmetry. But in the sixth and last stanza, the tone of the poem shifts. And it's God who is defined by the nature of the tiger. So I feel that the poet has a touch of Einstein's thought about, quote unquote, knowing the mind of the creator. Thank you.